So I like spending time on making the first slide, tweaking it endlessly until it's just right. But finding the style I'd like to commit to, that takes time. And usually I find myself exploring less creative options than I would like to. So I decided that this time I'll make a few, but very different. So I started with this one. I was like 100% sold, but it was like okay. But I like the sketchiness of it. So I thought maybe more like this. So I tried another one, but maybe use more fuzzier letters. Or maybe add more color. Or maybe Van Gogh Starry Night vibes. Or an actual starry night. But it kind of looks sleepy, so more powerful, with fire and aggression. Or chilled winter forest. But yeah, as you probably could have guessed by now, each image is generated. And each image you see took only 20 seconds to make, with texture synthesis and remixing from a single example. So my name is Anastasia Opara. I'm a procedural artist at Embark, and I'm very excited to be presenting for you today. So in total, I batch generated about 3,000 intro slides by having a library of roughly 150 images as examples. And I also made 6 guide maps, which were to dictate composition and contrast. And then I just let texture synthesis run while I was doing something else. And then I came back and just cherry-picked what I liked. And this ability to explore so many ideas and combinations quickly, and the thrill of finding combinations that would work, and just seeing what happens and where it can take me creatively, that was a lot of fun. It was like a visual brainstorm on steroids. And the main principle of the algorithm is not very complicated. Every pixel simply asks, if this is my neighbor's, what is my color? And the answer to that question is the example image we provide. So the image itself is a program that every pixel follows. But hey, does it mean we are programming by giving an example? And the answer is yes, and that is why I think example-based synthesis is so interesting. Oh yeah, and you can make pretty trippy GIFs by generating a couple of variations. At Embark, we believe that it should be as easy to create as it is to play, which requires us to rethink the way we create today. And I believe one way to approach the vision of accessible creation is by enabling to effortlessly sculpt and navigate creative possibility space. So what do I even mean by sculpting possibility space? Tools define our workflows. That is why one of my main fascinations with proceduralism comes from the power to define what I artistically want via a set of rules. So I basically encode my own artistic process and decision-making into an algorithm. And that algorithm, in turn, outputs a space of generated outcomes that are following the rules I described. And I can sculpt that space by manipulating the algorithm. And as a mechanism for navigation through that space, I can add sliders or other parameters that treat it as inputs to my carefully designed functions. But tools requires a lot of knowledge, which is often orthogonal to content creator skills. And it also requires to disrupt creative flow and step into translate what you want so the program understands mindset. And it's also time-consuming. But imagine if we could define a space of possibilities by providing examples of what we want and have a program extract relevant rules from these examples. Then we can immediately jump into the exploration of the generative space without needing to manually craft the points we're exploring or the algorithm itself, thus always staying within the creative iteration loop. And in the end, we will probably converge on a point we're satisfied with. And this point in this malleable by example space can be reused as an example for the next space we or maybe someone else designs. And because of the example-based nature, these spaces have a format intuitive to both read and write, meaning that content creators will be able to create their own tools by doing what they already do best, making awesome stuff. And of course, getting to that workflow is a long journey. And even though we have ideas on how to get there, we don't have all the answers. And it is most likely not the answer, but a piece of an overall puzzle. And we are at the very beginning of our exploration, where texture synthesis, the topic of this talk, is just a small step towards that bigger vision, where ultimately we are interested in creation of full 3D interactive experiences. So now that you have a bit of whys, let's talk about technical hows. So how does texture synthesis work and also a brief and totally incomplete history of non-parametric texture synthesis. So when working with procedural systems, I often design a top-down hierarchical approach where I determine a strict sequence of generator chains, which operate in a dependency isolation from one another. So let's say that we want to make a procedural house. We would start with generating a silhouette, and that silhouette would issue commands for other generators to be placed. But before it would pass those parameters to doors, windows, and other modules, it would determine locations and handle all dependencies. So the next generators will receive information that is unaffected by other generators' outcomes. So when, for example, the door module is generating knobs and wooden planks, we can be quite sure that it would not suddenly mess up the chimney. And that allows us to break down a complex task into smaller, manageable chunks, which is amazing if we are only interested in top-down questions, such as, if this is my silhouette, where are the windows? However, if we ask a reverse question, if the windows are here, what is the house? The generator would not be able to answer. But what would happen if, instead of having a hierarchy of commands, we would have a self-organizing system of simple elements where each contributes to a collective emergent decision? And to make the explanation a bit more approachable, I present you your hosts. Meet the color blobs of Pixel Town. They are extremely social beings who love to hang out together and coordinate their colors together. And they are looking for a new home. And so happens that we are about to synthesize a whole bunch of new pixels for a new image. So let's imagine that the image we want to generate is, in fact, a perfectly grid-like Pixel Town, where every pixel cell is a house waiting for a color blob occupant. However, we have a specific visual goal in mind. We want to generate something that looks like an example image. So how do we communicate that to the color blobs when they start moving in? Well, we provide them with an example image itself, but deconstruct it into neighborhood patterns and the corresponding pixel colors that should be placed if a specific pattern is encountered. You can think of it as an instruction manual that tells each blob what colors they should be if their neighbors are in particular color combination. So in this example, if my neighbor is light green, I would also be light green. If it's like darker green, I'm also dark green. And we have a lot of this kind of rules, basically as many as we can break the image into. And here is just a visualization of deconstructing an image into 3x3 neighborhood patterns. And as you can see, even for an image of 50 by 50, it is quite a few patterns in our manual. But how do pixels, or color blobs, even use all these patterns? So let's investigate a concrete example. So here is Bob. Bob's a blob, and he plans to move into the Pixel Town. But before he can do that, he needs to know what color complements best to his existing neighbors. So he goes around his neighbors and records everyone he saw and in what order. And if no one moved in, he also checks that. So what Bob does is a construction of his neighborhood color pattern. Then Bob checks his manual. He goes through the list of all possible patterns. And let me remove actually the neighbors that are not present, so you can see easier. Yeah. And as you can see, it might so happen that there is no exact match. But that doesn't stop Bob, as he decides, oh well, I will try to follow the manual as best as I can. So Bob chooses the closest matching color pattern to the pattern of his neighbors. And sure, the purple is a little bit off. It's like more brown in the example. But hey, otherwise it's pretty close, and that's good enough. So Bob takes the color associated with that pattern as his final choice and moves into the Pixel Town, and everyone's happy. And then Mary moves in, and now she does exactly the same. And she will partially base her choice on Bob's color choice because now he is her neighbor, and she knows that she can trust him since he followed exactly the same manual. And so this process is repeated until the whole town is full. And through this repeated local behavior, the resulting generated image emerges to be perceptually similar to the example image. And I say emerge because individual pixels are never actually aware of the full picture they are part of and have no knowledge of the example image as a whole, but just a disjoint collection of pattern rules. So this technique was first proposed in 1981 by Garber, but discarded due to computational intractability at the time, and then proposed again independently 18 years later by Efros and Leung in 1999, and became an origin of a whole subfield of texture synthesis called non-parametric texture synthesis. And it was also my first implementation in the texture synthesis journey. However, the proposed method was not perfect. First of all, it was very slow. For an example image of just 100 by 100, it is 10,000 pattern examples that have to be checked by every pixel we synthesize. So if we are generating just a 100 by 100 image with a pattern of 12 neighbors, that is 1.2 billion queries in total. Secondly, if a pixel doesn't have a good matching pattern to follow, it is still forced to make a decision what color it should be, no matter how bad the decision turns out. But that in turn means that the following pixels will also be more likely to make a poor decision, as they will be influenced by the previous decisions. Thus, it creates a chain reaction of poorly chosen pixels, resulting in garbage growing. As you can see in the example on the right, we have places where details are completely lost and become smudged, uncertain mess. So one of the solutions to address problem number one, the slowness, was tree search for the closest matching pattern. And it was proposed in fast texture synthesis using tree-structured vector quantization. However, the technique has a requirement for all the search queries to adhere to the same format. Thus, you could no longer have an arbitrary pattern of neighbors, it had to be fixed across all pixels. So a scanline order became a natural solution. Another contribution from this paper, which was used before in texture synthesis, but now with non-parametric flavor, was multi-resolution synthesis, where you decompose the example image into an image pyramid, which is the same image but at multiple resolution scales. And we generate starting from the lowest resolution all the way to the highest, conditioning each level on the previous one. And the intuition behind this is that by having some information from the previous level, that kind of sort of gives you a general idea of a bigger picture around you in the current resolution level. And quite a curious property of this algorithm is that you start generating from noise, which is refined to look more and more plausible through multiple resolution levels as more and more details are being synthesized. Or if you want to add AI vibe to this, you can say that the details are being imagined from noise by the algorithm. But no, it's just plain best fit search. So here is just a small demonstration that no matter what image we start with as our lowest level of pyramid, so here's like a ferrofluid, some kind of Christmas bauble, and rust, we will always end up looking something like the example image, because those are the only patterns available to the algorithm to operate on. And I guess one can treat this as a sort of funky style transfer with image pyramids. So coming back to the garbage growing problem. A series of patch-based techniques were proposed, as it was noticed that very few pixels actually had multiple choices of what they can be, and often are completely determined by what has been generated around them. Thus, the logic is, why waste compute power on synthesizing individual pixels when we're inevitably copying bigger patches anyway? So let's just shortcut to copying patches and then try to hide seams between those, kind of like a mosaic or a jigsaw puzzle. And then there was another very interesting technique proposed in synthesizing natural textures that kind of touched on both the speed of the search as well as patch-based synthesis. So what we do is we ask each of our neighbors, already existing resolved neighbors, where did they come from in the original image? And based on that, we determine our candidates. So in a way, every neighbor makes a suggestion of what the next pixel color should be. And then we also add a couple of random candidates from the example, and it's just in case all our neighbors had just terrible ideas. And the result is not just massively sped up search, since we greatly reduce the number of candidates, thus the size of our manual, but also since in many cases we are going along with neighbors' suggestions, we are effectively copying patches, but in a very irregular shape, avoiding obvious seams between those patches. So kind of an example on the right that marked the borders between the patches. And since there are only dozens of patterns to pick from, we are no longer dependent on a tree structure search to do it fast. Thus, we do not really care for a scanline order anymore. In fact, the resolution order can be completely arbitrary. And in his dissertation, Image Texture Tools, Paul Harrison proposed, let's do it at random. And it is very curious because it is implicitly multi-scale. So why is that? Let's imagine that this is our image being generated. Pink-purple cells are resolved pixels, and orange is the pixel being resolved right now. And let's say that we are checking for 3 closest resolved neighbor as our neighborhood pattern. So in the case of iteration 20, since not so many pixels have been resolved yet, we have a big search radius, meaning we capture more global, further away information, but it is also rather sparse, opposed to iteration 200, where our 3 neighbors are much closer to us, resulting in a tighter search radius where we only capture immediate but also more frequent information. And as more and more pixels get resolved, our search radius shrinks. So kind of naturally, we go from big, sparse search to a smaller, local one. And the second idea introduced with image texture tools was, okay, let's say our initial color guess was far from ideal. We didn't know much at the time, and we based our color on very few faraway pixels. But now we are not fitting in with the new pixels that have just been generated around us. But this is fine, because we can choose again, and then again, and again, as many times as you perform what is called backtracking. So here's a comparison of generating the gradient image on the right with and without backtracking. And as you can see, without backtracking, we have to stick with our initial choices, no matter how bad they are. And our uncertainty, which is basically the error of the chosen pixels, stay unchanged. Opposed to the backtracking version, where we're able to reduce the error by choosing again based on the new information around us. So this is an example of a generated image. And we can get a couple of nice visualizations, such as places of uncertainty, which are usually located where the copied patches meet. And those are highlighted with different colors in copied patches visualization, and basically indicate that the whole area, marked with the same color, has just been straight copied from the example. And that also gives a nice intuition to what is happening, which you can think of as mixing the image up and gluing the patches together as best as possible. And this is how the resolution process looks like in action. And at this point, this was already my fourth Python prototype of texture synthesis. And it was the version I decided to take further, as both its implicit multi-scale neighbor search as well as ability to correct mistakes looked quite promising. And Tomasz Stachowiak and myself had a couple of contributions that we added along the way. First of all, we noticed that because of the algorithm's stochastic nature, during early stages of resolution, the sparse neighborhood information can be misleading. So let's say that this is our example image, and we have only so far generated these 3 brown pixels. Now, if we want to resolve this pixel in the red cell, we have a bit of ambiguity of whether it is a house or a tree. And if we look at the candidate pattern on the right there, well, they're completely the same for both the tree and the house. So what do we do? And it might so happen that this will just have a patch of the house and the tree trying to fight with each other, and kind of results in a very obvious seam, as it will just try to blend between them. So our observation was that in the beginning, you don't really care for specific pixel colors. You care more about the global distribution of stuff in the image making sense. And that is why we start with generating a blurry version of the image, where a lot of pixel values are averaged out with their neighbors, thus sort of encoding information about their surroundings. And then we progressively switch to sharper version of the image as we have more and more resolved pixels. And this way, for example, in this house and tree case, we avoid the ambiguity, as we can clearly see that the tree is more brown-green than the house, which is more like brown-red. And here is an example of the resolution stages of the algorithm itself. And we can also control how many of those levels we want to go through and how much % of total image is resolved at each stage. And when comparing to vanilla version, we noticed much better remixing, as the vanilla version hangs on to details already at the early stages, which results in it trying to stitch multiple islands only at later stages, and that creates more obvious seams, kind of like in the example of the water and rock here. Whereas the multi-resolution forces it to consider more global distribution from early on, and we also get much more interesting style transfer results, as it preserves more original style features, such as flowers in this case. But after style transfer testing, we noticed that the increased neighbor count yielded worse results than staying within a range of like 20, and we hypothesized that it might be due to all neighbors, no matter how far or close, were weighted equally. That means that once you have a lot of neighbors, there are more further ones than the close ones, and that skews the generator to satisfy the majority, thus sacrificing the immediate neighbors in favor of dominant distant ones. And the solution was rather simple, actually even used in the original non-parametric texture synthesis paper, of weighing each neighbor based on its distance to the pixel we want to resolve. And as you can see, especially with style transfer, we drastically reduce the garbage generation, which is this just same color-ish, and on the right we get much better pattern. So last but not least, here is a table comparing all the non-parametric implementations I did and times it takes for various image sizes. I tried to keep the settings as similar as possible to have a fair comparison, and settings between these last two are identical. So being evangelized by my colleagues, I re-implemented the random order algorithm in Rust programming language, which out of the box was about 20 times faster than Python. And then together with Tom, over the weekend, we just did a bunch of micro-optimizations, such as using r-star tree for nearest neighbor search when constructing the neighborhood pattern. And Tom also added CPU multithreading, and because the algorithm is stochastic and pixel resolution does not strictly depend on what has been synthesized immediately before, and even if it does, a lot of errors will be corrected in backtracking, it was pretty straightforward to multithread. So overall, it was a pretty massive speed up from my first implementation. And now with our latest version, we can get a 500 by 500 image in just 2.5 seconds and 1K in under 10. And that is if you're generating the whole image from scratch, because you can also just generate a part of an image, and it is going to be even faster as it mostly depends purely on the number of pixels you need to resolve. And to summarize this section of the presentation, I would like to take a moment to marvel at how you're really always building on the shoulder of giants, and the work that has been done before enables and inspires to do something new. And this is just our small and humble addition to the chain of really awesome ideas. But now, let's talk about how texture synthesis can be used. And I like to think of the use cases as artifacts of an archaeological expedition, where we have the ultimate goal, but we also discover a bunch of interesting stuff along the way that we can already use today. So first and foremost and most obvious, we can generate new similar-looking images from an example image. And we even have a pseudo-deterministic seed. Well, it is pseudo because of multi-threading, as we cannot guarantee which thread picks up which pixel. But generally, you almost don't see the difference between the outcomes. And I guess in practice, you can probably use this feature as find 10 differences puzzle generator, but super hardcore mode. We can also guide the generation by providing a mapping in a form of guide maps, which are abstract low-effort images, either black and white or RGB. And you can map a certain part of the image to be circular or any other shape, like the example on the left, or doing a more involved semantic guidance. So in this example, asking for 2 windows and a different shape of ivy. And it is quite convenient because you're manipulating a higher abstraction level than the image content itself. And this kind of guidance can also be generated automatically to produce a style transfer type of effect. So what we are basically doing is we generate guide maps as luminance of your target and example images, and then we do some histogram matching and use the same process as in the previous slide. And if you're like me and Tom, you can sink the whole weekend generating Tom's faces, because it is that addicting. But apart from that, we were actually quite impressed with the algorithm ability to preserve style features and remap that to still resemble a face. And you can also control how much style versus content you would like. So you can go from 1, which means you want to fully preserve the original content, or you can lower it, which in the context of the algorithm just means how much it weighs the cost between style and content when choosing best candidate. And this is controlled by alpha parameter, which is also adaptive, meaning the more pixels gets resolved, the smaller it gets, until we don't care for the original content at all, meaning we just put that value to 0. And that is done not to penalize smaller detail creation in the later stages. But moving on, we can also do tiling textures. We can either synthesize one from scratch, like in the example on the left, or we can edit the original non-tiling texture and make it tile, like in the example on the right. And the most exciting feature is the variations of tiling you get. Like in the flower image, in the place of the seam, we can either have some dark vegetation or a white flower, and both make sense. Or we can ask to generate again and get something new. We can also fill in missing information. And again, we get a bunch of variations pretty much for free. And even when a lot of information is missing, like in the bark example, it is still able to plausibly restore the image from the existing data. And it is not limited to generation from a single example. We can have multiple examples, which can be used to mix multiple images together. So the visualization on the right of the map ID kind of gives you a hint where different colors represent patches coming from the different images. But let me show more explicitly what came from where. So this part came from there. Or should I give you time to guess and try to find the similarities? This one is from here and here. And just showing the original again without the markings. And we can also start layering all of those verbs we just went through. So how about multi-example guided generation? Here I'm generating 30 new Russian Nalichnik windows from only 5 examples and corresponding guide maps. And then I ask to basically transform those images and mix them in such a way that obeys my target guide map, which is this one. And to help generation a little bit, I include spatial information in the form of a gradient in a red channel. So as you can see, it goes from black to red. And oh yeah, and I also generate only a half, so I mirror the image. And this can be quite a neat workflow for exploring variations out of very small data sets. And why be limited only to 2D? We can do 3D as well if we can represent it as a texture data, such as displacement maps. Then just from a single rock example, we can generate more using the same texture synthesis code. And in order to correlate displacement data with color data, we set it up as a hierarchical generation, where we first generate displacement, guided by user-created guide maps, and then we generate color that is guided by the displacement maps. Therefore, the color is aware of the shape of the rock, so we naturally get dirt in the creases, grass on the flatter areas, and so on. So those dependencies are automatically captured for us. And imagine if we had a bigger library of rock examples, then our remixing capability would be even greater. Our artists have used texture synthesis for some of their terrain workflows, where they start with large-scale terrain later scanned data. But it comes with a lot of undesired elements, such as shadows, roads, and trees. And texture synthesis, together with Photoshop's content-aware fill, can be used to clean that up. Content-aware fill on its own is a good average color filament, but as Pontus Rumen points out, texture synthesis can provide high-quality details that you can't get otherwise. And then Pontus had a really cool idea that we can use the difference between before and after to extract the actual placement masks for in-game assets, such as trees. So here's just another example of before and after. And this is, by the way, 16K image. So it takes a while to generate, ranging between 10 and 15 minutes, which is not real-time workflow, but it is still vastly faster than doing it manually. And then we can have a nice coffee break while it does the work for us. Okay, so here's just a snippet of our internal show and tell about the terrain.
What you're looking at is our first environment test. The purpose of this test was to see how far we could push the size and scale of our worlds with a small team using smart techniques and tools. This is a 256 square kilometer terrain with another 3,000 square kilometer backdrop to add to the sense of scale. To build it, we used laser scan terrain data and satellite imagery. With our own in-house tech, we filter out unwanted data from the ground surface satellite image, like bushes and trees. We then used our internal texture synthesis tool to procedurally generate replacement data and added real 3D assets to populate the world. Combined with the procedurally generated snow and weather system, the result is an environment that feels lifelike and dynamic, filled with naturally placed rocks, grass, bushes, and roots.
And just a note that Pontus asked me to make. There he says texture synthesis is used for placement, but what he actually meant is placement masks that we use already for placing. Okay. And by the way, if you want to see more of the crazy awesome work our artists are doing, I recommend checking out our museum blog post, where they showcase our first environment test and also talk about photogrammetry workflows. And speaking of photogrammetry, another application of texture synthesis is filling in missing information from photogrammetry, where often we are missing a chunk of mesh due to its inaccessibility during the scanning process. So let me show you our very first version, 000001, prototype for automatically detecting when it happens and filling in both mesh and texture data. So we start by receiving a scanned asset with, in this case, 3 maps, though this number can be arbitrary, and a missing chunk of the bottom. So we use Houdini to fill in the mesh hole and mark it with white to indicate that this is the part of the mesh that needs texture synthesis. And the user can also additionally paint the areas they would like to regenerate. So let's say there is a part that they would like to remove or just have a different variation. So in this case, the user marked 2 parts, one on the top and one on the side. And here's how the process looks like in action. For each marked for generation island, we create its own in-painted map that is unwrapped in a continuous way to ensure no seams between original and generated textures. And to make sure that all provided maps match, we also record a history of what texture synthesis did and apply exactly the same transformation to all of the maps. So in this log example, we get 3 maps and they match perfectly between each other. So if one of them was like roughness, for example, it would go naturally with the color information. And now you can see the final texture synthesized high poly mesh with color map applied. And the synthesized parts fit seamlessly with the original texture. And this is how the original color map looked like. And this is just a comparison between the two. And then we can just use this high poly mesh and proceed to baking it into low poly, just the way we usually do it. So now, I'd like to talk about some of the limitations of this approach. First of all, it's pretty bad with complex semantics that go beyond pixel color, unless you use a semantic guide map, like in the window generation example. Otherwise, it has no understanding of what it's generating, so you might end up with pretty logical themes, but the algorithm would insist that they totally make sense from purely local neighborhood perspective. Second limitation is that it's not that great for textures featuring a very precise ordered patterns, because then it has trouble stitching it together due to stochastic resolution nature. Increasing neighbor count helps, but even then you will most likely get discontinuities in the outcome. It also cannot infer new information, so it only operates on what's already there in the example image. So in this example on the right, it has trouble blending the blue corner because it has no example of how it can be blended in that particular situation. The symptom of which we can also observe in the uncertainty map, where most red is concentrated around that corner. But at the same time, if we investigate copied patches map, we can see how much remixing went into the left side of the image. So it can become pretty granular, which intuitively you can think of it really had to come up with something new, since it doesn't have a precise answer in the example. And that doesn't necessarily mean it will fail coming up with something plausible. But a bit more illustrative example of this limitation is asking to continue a half circle on a gradient background, which it completely fails because, first of all, it doesn't have examples on how curvature looks like on the other side of the circle. Plus, it doesn't separate circle from the background. So for the algorithm, those are inseparable concepts that only exist together, like in the example image. That is why in the zoomed-in image, it went with darker blue, because it probably sampled those pixels from the top of the circle, and that's the top, so it always goes with dark blue. That's the only example it has. And we can see its uncertainty manifesting itself in this very noisy border between yellow and blue. And last, this algorithm is designed for small data sets or single exemplars. If we have a library of 1,000 images, the likelihood that we will use a better sample from a particular image becomes more unlikely the more images we add. Because in most cases, the algorithm will go along with neighbor suggestions, thus completely eliminating using too many example images. However, it doesn't mean it will not benefit from having more examples at all. It just means that the likelihood of remixing a lot of images is very small. So you are more likely to end up with something like 3 or 5 images used of the total 1,000 you might provide. To summarize, we have talked about the vision of accessible creation, and that one way to approach that is with example-based synthesis that allows anyone to describe their own generative possibility spaces. We talked about how texture synthesis works, where every pixel is programmed by your example, and by interacting with each other, pixels emerge to look similar to the example image. And we went through some use cases and all of those verbs, such as guided, multi-example, single example, in-painting, tiling, and how a combination of those verbs can be used for terrain workflows, geometry generation, style transfer, and photogrammetry cleanup. And then we also touched on the limitations of our texture synthesis approach to highlight that it is not a silver bullet for image generation. As for the future, I firmly believe that the next step for creative tools is the ability to generate program representations from our creative intent. So sort of like frameworks that can be filled with auto-inferred rules from our creative intent. As for our own research, our next step is example-based is moving towards 3D. We already started looking into inverse procedural modeling, where procedural rules are created from examples, and even have very first baby results, but that's maybe a talk for the next year. And if you're interested in digging deeper into non-parametric texture synthesis, here is a list of references used in this presentation. And I think we're going to upload the presentation online, so you can have a closer look then. And before we wrap up, I would like to give a shout out to the whole Embark team. This image is not really representative anymore since we welcomed so many new faces in the past months. But I just want to say that it's an absolute pleasure to work with such talented people on the topics that I deeply care for. And that would be it. And I would like to thank you all for listening. And if we still have time for questions, I'd love to hear them.